Okay, so let's get started. So this week in review, what we're going to do today is we're going to look at higher order derivatives. Okay. On Wednesday, we'll shift gears and we'll look at tangent and normal lines. Both of these sections should be kind of like a review. I mean, we've talked about higher order derivatives before. The only new twist in this material is that you're going to have chain rule and implicit differentiation, right? And maybe product and quotient rule, but the idea is the same. Tangent lines we've already talked about, and normal lines are just lines that are perpendicular to tangent lines. So we're gonna utilize the facts that we learned in the first module about the relationship between perpendicular lines, right? And Friday, I'm just going to make an open session. So we'll probably finish all of the course material by Wednesday. And if you have questions, I'll just leave it open to you, whatever questions you have. And if you don't, then, you know, we have the day off, right? So higher order derivatives. So what it means to have a higher order derivative is it just means that you're taking the derivative repeatedly.
I don't believe you're screen sharing if you're writing something.
I am, thanks. Let me go back and see here. Give me a second. Taking a little while because I have a video that's rendering, so a little slow. There we are. Okay, thanks. Here we go. See, it shows that it's on, but for some reason it's not. Sometimes it is, sometimes it isn't. So thanks for catching that. Okay. So higher order derivative just means that we're, repeatedly taking derivatives, right? So it just means that we're repeatedly taking derivatives. And so if you're looking at, for example, say what we normally call the derivative, right? So we could make here a little table, the order of the derivative, the notation that we use to represent it, and where we might see this in applications. So the first order derivative is what we're usually referring to when we're talking about a derivative. And of course we have our prime notation or our operator notation. And the only real first derivative that you're going to have to know as far as applications is the velocity. Right? So we learned that the velocity is the first derivative of the position function, the displacement function. And so the second order derivative just means that we're taking the derivative of the first order derivative. So this is going to be the derivative of y prime, which we write as y double prime. And if we use the operator notation, it's going to be d squared y over dx squared. And of course, we said the application of the second derivative that we're going to come across is the acceleration, which is the derivative of the velocity function or the second derivative of the displacement function. And there are higher order derivatives. So the third order derivative in physics is the jerk, and the fourth, fifth, and sixth are called snap, crackle, and pop. I'm not joking. Apparently someone liked Rice Krispies. And you can go down to the nth order derivative, and this is generally written as y to the nth of x. or d to the nth of y, dx to the nth. And generally in applications, you never see greater than the sixth order derivative. When you're looking at beam bending problems, you see the sixth order derivative, but I've never seen a problem where it's higher than sixth order. So they don't go very high in most physical applications anyhow. So questions that we have on the basic notion of a derivative or any sort of notation. Good. And I'm going to work some problems now that are kind of like the homework, okay? So the first question here asks, how many derivatives would you have to take to get the equation to become zero? Well, it's not actually quite the correct way of writing it. I mean, right, they want to ask, how many derivatives do you need to take until the derivative becomes zero? Okay, the derivative function becomes zero. So they want to know what is the order of the derivative, the smallest value of n, such that the nth derivative of y is equal to 0. Okay? And so if you look at it, every time you take the derivative, I mean, let's just look at the first derivative, right? So the first derivative becomes 91x to the 91 minus 1. And so we'll notice that by the time we get down to the 91st derivative, right, we're going to have a constant function, right? You're going to have 91 times 90 times dot, 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 all the way down to 1 times x to the 0. Because if you have 91 apples, right, and each time I go in and I take one apple, by the 91st time, you're going to have 0 apples left over. And so this is just going to be a constant. This is actually something that in math we write as 91 factorial. I don't know if you guys came across the factorial function yet. But that's all it is. This is just a constant, right? So when I take the 92nd derivative, I'm going to get 0. And people generally write this so that they don't confuse this with an exponent. They generally write this in brackets or parentheses, okay? Because they don't want people to think this is y to the 92nd power, okay? I'm going to get 0. Okay, so my answer is going to be 92. You have to take 92 derivatives. Now, sometimes, you know, when you're kind of doing this, sometimes people they get a little tricked up, right? Like, how many times do I have to take it till I get down to x to the 0? Sometimes what you can do is you can solve a simpler problem, right? So, you know, one way that you might do this also is you might try a simpler problem. Like try y equal to x cubed, right? And if you do that, you'll see that y prime is proportional to x squared, right? And y double prime is proportional to x to the first. And y triple prime is proportional to a constant. So this tells you that your answer has to be 4. And you notice, of course, that 4 is 1 more than the value of the exponent. So then you might use that as a guide for your intuition on this problem. Does that seem okay, or do we want to discuss anything more just to make sure everyone's good on that? All right, very good. Okay, so now we want to go ahead and calculate. I don't know if I'd use the word calculate, but you want to find the second derivative of this function. Okay, so first we're going to find the first derivative. First things first, right? And I look at this, and there's nothing here that makes me worried, right? I have a sum, so my form is a sum, and it's a sum of power functions. So I know that this is going to be pretty straightforward, right? So y prime I'll just take the derivative of each term, right? So I will get 6x to the 5th minus 5x to the 4th minus 16. So now to find the second derivative, I just take, so second derivative means take the derivative twice, right? So find the second derivative of y just means take the derivative twice. So now I just take the derivative one more time. And this shouldn't be a big surprise. I mean, you know, the derivative in and of itself is a function, right? So it's not that crazy to think that I can take its derivative, right? So I'll go ahead and do that. And with polynomials, of course, it gets easier and easier, right? Because the exponent just keeps decreasing and some of these terms go away. So I'll bring the 5 down and have 6 times 5, which is 30, times x to the 4th. And the derivative of the second term, I'll bring down the 4. So I'll have 5 times 4, which is 20 times x cubed. And of course, the derivative of negative 16 is the derivative of a constant, which is 0. And so this, my friends, is my final answer. Okay. Questions before we go on? Everyone's good? Okay. So now they want us to do an application. Now they're going to ask us to find the acceleration. So we're just going to take the derivative twice. So the first derivative, same sort of deal, right? I have a sum of power functions, so that's not going to pose a lot of problems. So for the first term, I'll bring down the 3, right? And I'll have a minus 8 times 3, which, if my calculations are correct, is 24. And taking 1 away from the exponent, I'll have a squared. And of course, 217 times t just leaves me 217. And now we'll take the derivative one more time. And so 2 times 24 will be 48, and I have a negative sign, and I'll have t to the first. And that'll be my final answer. Now, one word of caution, don't necessarily expect them to tell you that the acceleration is a second derivative. So this is something that on an exam, they will expect you to know, right? They're not going to necessarily tell you. They might just say, find the acceleration, and you're supposed to know that the acceleration is the second derivative, right? So this is something that you should know, that the acceleration function is the second derivative of the position function. Especially, you know, working with, you know, airplanes and all, acceleration's like a big deal, right? Okay. Okay, so here they want us to calculate the second derivative of this function. And so, again, you want to look at the form, right? So what is the form here going to be? So if I look at the last thing I'm going to do, do I have a sum, a difference, a product? What do I have here going on? Do I have a function of a function? So am I looking at a sum, a difference, a multiple of a function, function times function, function divided by function, function of function, or a function of y? Which of these do I have? So So hopefully by now it's obvious that you have a function of a function. So I know the form that I'm going to use is the chain rule here. That's what I want to start off recognizing. And so I'm going to go ahead, I'm going to write this as y prime is equal to, so my 4 I'm going to pull outside, and I'm going to have ddx times 4 minus 3x to the 4th. And so to take the derivative of this, I'm going to think of this as we were thinking of this on Friday. I'm going to think of the inside function as blob, which I'm just going to write like this. And if I put in blob, right, for this, the inside function, which is here, the outside function is going to be blob to the 4th. So I'm now going to think about this as d dx of blob to the 4th. And the chain rule tells me that the way to evaluate this is to take dd blob of blob to the 4th and multiply that times d blob dx. Everybody should recognize that this first derivative is 4 blob to the cubed. Okay, whenever you're taking the derivative of a power function and the variable you're taking the derivative with respect to is the independent variable, you can use your power rule. So this will be 4 blob to the cubed, sorry. And the blob here is 4 minus 3x. Okay, and of course, when I do that, I'm going to get a minus 3. So when all the mathematical smoke clears, I'll get minus 12 from the minus 4 here and the minus 3 here, and I'll substitute in for blob, and so I'll have 4 minus 3x all raised to the 3rd power. And I'm going to go back now and substitute that in. So this will be 4 times negative 12 times minus 4 minus 3x to the cube. Oops. Okay. But I'm not done. So make sure that you answer the question. They want the second derivative, so I have to take the derivative again. And so when I do, I'm going to be playing exactly the same game, right? I have the same sort of situation. I have a number times a quantity raised to a power, so I'm going to have to use the chain rule again. And here we're not going to do this off to the side. We're just going to try to do this without, a lot of extra work. So this is blob to the 3rd. So the derivative of blob to the 3rd with respect to blob is going to be 3 times blob squared. And the derivative of blob, which is 4 minus 3x, becomes minus 3. Okay? And now when we put this all together, right, so you're going to go ahead and you'll multiply out all the numbers there, right? So you're going to get a positive 432 when you multiply 9 times 48, and these two negatives become positive, right? And times the quantity 4 minus 3x squared. And then this will be your final answer. When you have quantities raised to powers, do not expand them. Okay? So when you have, like polynomials raised to powers, don't expand them, okay? We don't want to do that. All right, so before we go on, questions? Everybody's good on this? Okay. So moving on. So now they want the fourth derivative, okay? Now I can tell you, like I said, I don't make up the exams, but I can tell you that teachers like this sort of problem because it tests three things. It tests whether you know that reciprocal powers are written as negative exponents. It tests whether you know how to take the derivative of negative exponents. And it also tests whether or not you're careful with your algebra. And so I can tell you that there's a good likelihood this will be on here. So first I'm going to write the original function, but anticipating that I'm going to be taking the derivative, I'm going to write that reciprocal power as a negative exponent, right? So first I'll write y to the x is equal to 9 times x to the minus 1. And so now we take the first derivative. And of course that's going to bring down the negative 1, right? So I'll have 9 times negative 1. And then I'm going to reduce the exponent by 1. And you'll be surprised at the number of people. So I just said it tests whether you know how to take the derivative of negative exponents. You'll be surprised at the number of students who want to add 1. Okay, and that's part of what they're testing, right? So now I'll get minus 9 times x to the minus 2. And we keep on doing this. So when I take the second derivative, right? Got kind of excited and went too far. So the same sort of game, right? I'm going to bring down the negative 2, and the negative 2 times the negative 9 will be a positive 18, and that will be x to the minus 3. And one more time. Third derivative, right? So you bring down the 3, right? And you multiply that by 18. That's a negative 3 actually. So that'll be what? Minus 54 x to the minus 4. And now we're on the 1 yard line. Take the fourth derivative. And we're going to have minus 4 times minus 54, which is positive 216, times x to the minus 5th. And of course, you have to watch because this isn't how you'll see it, right, on the answer sheet. How will you see it on the answer sheet? What will be different? Instead of x to the minus 5, what will you see?
A fraction.
Right. I'm going to go back and bring him downstairs and make him positive. So we're going to write our negative exponents as reciprocal powers. Very good. And that is our final answer. And notice they could ask you to do this to an arbitrary number of derivatives. I mean, after a while, it would get to be a little cumbersome, but you could do it. It wouldn't be that hard. Let's see, any questions? That looks okay? All right, very good. Now, these are the sorts of problems that I was hearing about from people yesterday who were working on the homework. And So here, you look at this and you want to think about what is the form. Well, the form is first a product, right? And in the course of doing the product, you're going to have to use the chain rule on the second factor. And we're going to have to do a little bit more in terms of mathematics with simplifying this too. So that's going to be the hard part. So product rule, chain rule, and simplifying. Okay, so if we take the first derivative, so let's take the first derivative using the chain rule. Which I'm just going to abbreviate by CR. I mean product rule, sorry. I'm getting ahead of myself here, aren't I? Using the product rule. Okay. And by the way, a really good hack for the exam is to tell me what you're doing. And that way, if you do make an algebraic error, which is easy to make, myself included, at least I'll know that you knew what you were doing. So it's always a good idea. When in doubt, write it out. So I'm going to take the derivative of x squared first and leave the second term alone. And then with the x squared alone, I take the derivative of the second term. And see, this way, even if you make an error taking the derivative, chances are it's not going to be a huge deal. At least I'll understand you knew what you were doing, right? So, first term is easy. I'm going to do this one off to the side, okay? So we'll work this derivative off to the side. We're going to use the chain rule. So, d dx of 6x minus 7 to the third. So this inside function, the thing contained in the parenthesis is my blob. So first I'm going to take the derivative of blob to the third with respect to blob. So I'll get 3 blob squared. This is the derivative of the outer function. And the derivative of the inner is easy, right? It's just the derivative of 6x minus 7 with respect to x. So that's just going to give me 6. So I can go back and plug that in. Not a bad idea, again, when you're doing this, to have a kind of bookkeeping system. And when you're taking derivatives of complicated things, it's usually better to do it off to the side. And that way I can follow your work. It's not lost in this really already complicated expression. Okay? So I'm going to go back in, put that in, and, whoops, one derivative. And so the first term is just 2x times 6x minus 7 quantity cubed. And then this is x squared. And here I got 18 times 6x minus 7 squared. And I need, yeah, that looks good, okay. Okay, so now here comes the hard part. Like most things in life, there's an easy way and there's a hard way to do this. The easy way to do this is to realize that you can factor some things out. So I noticed that I can factor a 2 and an x and a 6x minus 7 quantity to the second power. So I can factor this out of each term. And then I can simplify the remainder. So I'm going to go ahead and do that. Now you don't have to. Notice that you could do the same thing again with the product rule and the chain rule, right? Each of these would be a separate product rule. And then each of them would also involve another chain rule. But this will make things a little easier, I think. So I'm going to take the 2x, 6x minus 7 quantity squared out. And what I'm going to have left, well, here in the first term, all I had was a 6x minus 7 left, right? And here when I take out a 2, I'll have a 9 left over. And take out one factor of x, and I'll have an x left over, and that's it. And so when all the mathematical smoke clears, right, I'm going to get 2x times 6x minus 7 squared times the quantity 15x minus 7. Is that looking okay? And what I'm going to do now, because if I don't do this, I'm going to have to take the derivative of a product of 3 quantities, which I can do. I mean, it's just an extension of the product rule. But instead of messing around with that, I'm going to put the x back in here. So I'm going to go ahead and I'm going to distribute the x. There's a little bit of algebra here, right? And so when you do that, you get y prime of x is equal to 2 times 6x minus 7 quantity squared times 15x squared minus 7x. And I'm not done. I have to take the derivative one more time. And so I'm going to use the product rule, right? I have a product of 2 things. So if I use the product rule, the first term is going to require that I use the chain rule on this. So it'll be y double prime. Hold on, my pen just gave out. Sorry, just give me 1 second. Okay. There we go. All right. So again, product rule, the first term's the chain rule. So I'm going to do y double prime of x. Now a little bit of bookkeeping advice here, okay? Notice this 2 I have hanging out here, okay? I could bring the 2 inside. I'm going to keep him outside, but if I do that, I'm going to have to put brackets, right? Because when I use the product rule, I'm going to have 2 terms, and the 2 is going to be multiplying both of them, so I'm going to have to be careful about that. So when I use the chain rule, the derivative of blob squared with respect to blob is 2 blob, and then the derivative of blob with respect to x is this derivative with respect to x, which is 6. And then, of course, nothing changes with the second term. 15x squared minus 7x. And now here, for the second term, of course, nothing happens to the first factor, right? So this just becomes 6x minus 7 squared. And now I'm taking the derivative of the second term, which is a sum of power functions. So this will just be 30x to the first minus 7. And now we notice that we have the same sort of game as before. I can simplify by factoring out a little bit, right? Unfortunately, in this case, I don't have a great deal I can factor out. All I can do is just factor out a 6x minus 7. But when I do that, I will have y double prime. Give me a second. Okay, there we go. So y double prime is equal to 2 times the quantity 6x minus 7 And if I look here, I'm going to have what? 12 times 15x squared minus 7x. And for the second term, when one factor of 6x minus 7 comes out, there'll still be one factor left. And so I'm going to have a little bit of foiling to do, right? So let's make a little room for that. And so the first term's not hard. I just distribute the 12, right? So I'm going to get 2 times 6x minus 7. And 12 times 15 is what, 180? So 180x squared. 12 times 7 is going to be minus 84x. And then we have to do a little foiling down here for the second quantity, right? So we'll have 6x minus 30x. So that'll also be 180x squared. 6x times 7 minus 7, okay, it's going to be a minus 42x. Minus 7 times 30x is going to be minus 210x. And finally, we'll have positive 49. Okay. And now we just have to be a little careful with the arithmetic, really, right? So this will be 2 times 6x minus 7. I have two 180x squared. So again, a good bookkeeping technique is to kind of have the same sort of notation for like terms, right? So when I check my work, did I get all the x squared terms? Yeah, these are the two that are underlined. And that will be, what, a 360x squared. And I notice that I have 3x to the first term, so this will be my little bookkeeping technique for this, right? And so this will be 126 and 2 10s, so that'll be 336. And I just have 149 all by itself. And that, my friend, appears to be the end. That's it. So what do we think? Anything we want to go back and look over, or does that look okay? Now that's a legitimate exam problem. Okay, and if you do it on an exam, I'll expect you to show your work. So I'll expect you to show all this. If I can't do it, so here's kind of the rule of thumb. If I can't do it in the same number of steps than you can, my assumption is you probably can't either. Okay, because I've done this a long time and I know the shortcuts. So again, work it out, take your time, and I'll be looking at your work to make sure. And the more you write out, the more chances you have of getting extra credit, because you could make a stupid numerical error like 12 times 15, right? You might say it's 160 or whatever. If you just go to the answer, I don't know necessarily that you knew what you were doing, but if you write everything out, I'll just ding you a little bit for that one little mistake. Questions that we have or things that we'd like to see and talk about a little bit more. Okay? All right. So, let's take a look at the last one. The last one's an interesting problem. It says calculate the second derivative for x squared plus y squared is equal to 88. So the first thing I notice when I'm thinking about this from the perspective of a form, right, is that I have a sum. Of course, this side doesn't even concern me. This is going to go to 0 when I take the derivative. I'm going to be taking the sum of two power functions, but this is a function of y, so I'm going to have to use implicit differentiation, right? And again, this is what you want to do. It's kind of like a game of chess or war, right? There's a certain strategy, and you want to get the lay of the land before you get into the heat of the battle. So if we go ahead and take the first derivative, I'm going to get something like this. And of course, the first and the last terms don't concern me, right? This is just 2x. The prime is with respect to x. And for the second term, I'm going to have to use implicit differentiation, right? So if we look at this term right here, d dx of y squared, we remember that implicit differentiation tells us to take the derivative of this with respect to y first, and then multiply by the derivative of y with respect to x. I think my pen doesn't like implicit differentiation. Right? And then we're going to multiply that times y prime, dy dx. And so, of course, a derivative of y squared with respect to y is just 2y times y prime is equal to 0. And I'm going to solve for y prime for reasons which might not be apparent to you initially, but I'm going to go ahead and solve for y prime. So I'll bring the minus 2x over here, and I have 2y times y prime. And when I go ahead and divide both sides by 2y, of course my 2's will cancel, and here I'll just get x over y, and I'll get minus x over y, right? You have to be careful with the signs. And here I'll get y prime. Now I do this for two reasons. First of all, notice that when I take the second derivative, I have a choice now, right? I could take the derivative of this expression up here, okay? So I could take the derivative of this equation here. Excuse me, my pen just gave out. Okay. Come on. Let's go to red. So you could do this here, or I could take the derivative here. Either way. Most people prefer to take this when they're taking the derivative again. But we're going to see that we still need this second expression for y prime. Anybody not with me? You want to go back and see anything? Everyone's good? Okay, buckle up. So now let's go ahead and take the derivative with respect to x of our first equation, which is just 2x plus 2y, y prime is equal to 0. And of course, this first quantity is not going to cause me any trouble, but this is going to be a product, right? So if we go ahead and do that, I have d dx of 2x plus d dx of 2y times y prime is equal to 0. Okay. Of course, first term doesn't pose us any problems. That's just a 2. And the 2 factors out of the second term, but now I'm going to have the product rule, right? So I'm going to have y prime times y prime plus y times y double prime. Okay? Because I'm using the product rule, right? Take the derivative of the first factor, which will give me y prime, multiply it by the function that's a second factor, then leave this term alone and take the derivative with respect to the second factor. And that's where I'm getting this from. And so if we go ahead and divide out by 2, right, I'm going to have 1 plus y prime squared. Go back here. Plus y times y double prime is equal to 0. And notice what I want. I want to solve for y double prime purely in terms of x and y. And I don't have that right now. I have this y prime in here that I have to get rid of. But I solved for y prime up here. It's minus x over y, right? So I can go ahead and substitute that in. So let's go ahead and do that. Oops, hold on. Pen went out. So go ahead and do that while I'm screwing around with my pen. Go ahead and substitute in for y prime and solve for y double prime. And let's see what you get. So you're going to get 1 plus minus x over y squared plus y times y double prime. Come on. Sorry, I'm going to switch colors here. Sometimes it helps. Okay, y times y double prime. Oh, come on. There we go. Okay. And now I can solve for y double prime, right? If I go ahead and solve for y double prime, and I bring everything over to this side, I'll have minus 1 minus x squared over y squared is equal to y times y double prime. And I can put everything over a common fraction, right? So minus y squared minus x squared and divide by y, and I'll get y cubed is equal to y double prime x. This is a good problem to practice. The 3 problems that I would practice is this one, that really long algebraic one, the x squared times 6x minus 7 raised to the 3rd power, and the other one about y equals 9 over x. Those are 3 good problems to practice for the exam. And if you know that, you're pretty much ready. Okay, we got 1 minute left. Good timing. Any questions before we end for today? Everybody's good? Cool beans. Okay, I will see you fine folks on Wednesday. You take care. All right, thanks.
Thank you.
All right. Yes, I do see it, Ryan.